Hello everyone. In the lecture today, we'll introduce the methods applied for the flexible pavement design on Ontario roads. Currently in Ontario, MTO developed MI 193 method for the design of the flexible pavement. This method is actually developed based on the AASHTO 1993 method. The Ontario adaptation of the AASHTO 1993 method has been widely applied for a lot of Ontario highways. Similar to the AASHTO method, in the adaptation, we also need to consider the load equivalency factor, truck classes, truck factor, and the percentage of the trucks within each classes. In addition, the adaptation will also introduce the Ontario truck models as an additional input for the design of the flexible pavement. Currently, the adaptation has been increasingly used by the MTO and the major road agencies in Ontario, and it is actually applied for a lot of major routes such as heavily trafficked city street collectors and urban expressways. In the method, if the heavy commercial traffic distribution is not available, then MTO will recommend to use the previous truck factor approach in the AASHTO method. Furthermore, MTO identified that a qualified pavement design engineer should be involved in the flexible pavement design when we use the MTO adaptation method. The table here summarizes the typical truck factors for different vehicle classes defined by the Federal Highway Administration, and this truck factor is also applied for the AASHTO 93 method. In Ontario, we also use some of these truck factors for the design of the flexible pavement. This table summarizes the typical truck factors for the major truck classes applied in Ontario highways. Basically, for 2 to 3 axle trucks, the typical truck factor is around 0.5, and it could be ranged from 0.05 to 1. That depends on the load of each truck. While for the truck with 6 or more axles, the truck factors could be as high as 5.5. and the range is around 2.0 to 7.0. Moreover, the lane distribution factor is determined by the number of the lanes in one direction and the average annual daily traffic volume for both directions. If the number of lanes in one direction is 1, then the lane distribution factor is set as 100%. For the number of lanes as 2 for one direction, if the ADT is less than 15,000, then the lane distribution factor is set as 90%. If it's higher than 15,000, then the factor is set as 80%. You can find out the settings for the other number of lanes and levels of the ADT. Basically, with a higher volumes and higher number of the lanes in one direction, the lane distribution factor will be smaller. The table here shows the recommended serviceability factors applied for the Ontario roads. Basically, the serviceability factors varies with the types of the road. In addition to the PSI, Ontario also defines the Pavement Condition Index, PCI, to show the serviceability value of the roads. Usually for the higher PSI, the PCI values will also be larger. In Ontario, for the 400 series highway and some other high-volume multi-lane highways, the PSI is set as 4.5 at the new construction for the initial serviceability, and the PCI is set as 95, while the terminal serviceability is usually set as 2.6 for PSI and 65 for PCI. If we are talking about the rehabilitation project, the initial serviceability is set as 4.1 to 4.5 for PSI and 90 to 95 for PCI. For the other type of the roads, the initial serviceability and the terminal serviceability values will be smaller. For the arterial highways, the PSI At the initial serviceability, it's set as 4.5, while at the terminal, it's set as 2.5. The local rows has the smallest initial and terminal serviceability values. For the new construction project, the PSI is set as 4.2 and PCI is set as 90 at the initial phase. At the terminal phase, is set as 2.0 for PSI and 50 for PCI. In Ontario, the pavement condition index is a condition rating for the pavement structure. Usually, the ranges from 0 to 100 with high values of PCI, the performance of the pavement is better. Actually, both PCI and PSI can measure the pavement conditions, but they are evaluated at different ways. Usually, the PCI is evaluated based on the distress type, quantity, and severity. The figure on the right shows the changes of PCI over the time. Here you can see that when the pavement condition is poor, the PCI will drop dramatically over the time. So usually we will conduct the pavement rehabilitation project when the PCI reaches to 60, which means it's between the fair and the poor conditions. If you apply the reconstruction project at the serious poor or failed pavement condition, then the cost of the project will be 4 to 5 times higher than that for the rehabilitation project at the fair and the poor pavement conditions. In the MTO adaptation of the ASHTO measures, the design reliability and standard deviation should also be considered. The table here summarizes the overall standard deviation and the design reliability for Ontario roads. Usually for the flexible pavement, the standard deviation varies from 0.44 to 0.49. For the rigid pavement, it's around 0.34 to 0.39. And the design reliability varies with the road types. For 400 series highway and other high-volume multi-lane highways, the design reliability for the flexible and rigid pavement are all set around 90 to 95%. For the arterial highways, it's set around 85 to 95. For the collector and the minor arterial highways, it's around 85 to 90. For the local roads, it's set as 80 to 90. The MTO adaptation also recommends some typical resilient modulus values for the subgrade materials. The table here shows the typical MR values for different soil types. MTO actually has its own classification about the soil types, which is shown in the third column in this table. The first column makes a brief description about each class of the soil. Basically, for the low category number, the resilient modulus will be higher, and this kind of soil will have better drainage conditions, and they are less sensitive to the first action. In addition, the subgrade conditions is also categorized as good, fair, and poor based on the resilient modulus values. MTO also suggests some typical values about the structural coefficient AI for the flexible pavement design. The table here shows the typical values for different materials, and these values will be applied for the estimation of the thickness for each pavement layer. The drainage coefficient is also defined by the MTO adaptation. Usually in Ontario, the unbounded granular materials will have 3 drainage conditions: standard, questionable, and inadequate. For the standard drainage condition, the drainage coefficient is set as 1.0. For the questionable condition, the coefficient is set as 0.9. And for the inadequate condition, the coefficient varies from 0.5 to 0.8. The MTO adaptation also provides some recommended K values, the modulus of the subgrade reaction, and this value is only applied for the rigid pavement design, which is used in the AASHTO 93 method. Similar to the recommended MR values in the previous page, the recommended K value is also defined based on the classes of the subgrade soils defined by MTO, usually with lower category numbers. The modulus of the subgrade reaction will be higher. The drainage coefficient CD is also specified by the MTO adaptation for the design of the rigid pavement, which will be explained in the future lectures. The table here shows the typical CD values under different drainage conditions and climates. There are two types of the climates for the rigid pavement design, dry and wet. Dry indicates that the precipitation is less than or equal to 508 mm per year, while for the wet climate, the value is higher than 508 mm per year. In this table, you can see that when the drainage condition is excellent, then the coefficient will vary from 1.15 to 1.2 for the dry climate and 1.1 for the wet climate, while for the very poor drainage condition, the coefficient varies from 0.8 to 0.9 for the dry climate and 0.7 for the wet climate. In Ontario, the chalk factors is different from the AASHTO method. We actually have already showed the typical chalk factors for the major chalk classes in the previous pages. Usually for the urban highways and minor arterial roads, the chalk percentage is around 4 to 10%. And among those chalks, in Ontario roads, almost 65% of them are the 2 and 3 axial chalks. 5% are the 4 axial chalks, 20% are the 5 axial chalks, and the rest 10 will be the 6 or more axial chalks. In the previous page, we know that based on the MTO MI 183 method, the chalk factor for 2 and 3 axial chalks is set as 0.5, and it's 2.3 for 4 axial chalks, 1.6 for 5 axial chalks, and 5.5 for 6 or more axial chalks. While in Ontario, we applied an Ontario chalk model, and it specified the chalk factor as 0.4 for 2 and 3 axial chalks, 2.0 for 4 axial chalks, and 2.0 for the 5 axial chalks, 5.1 for 6 or more axial chalks. We will apply the Ontario chalk model for the design of the flexible pavement. In addition, for most of the Ontario roads, the design life is set as 20 years. And with this design life, we can find out the growth factor with respect to different annual growth rate. For example, if the annual growth rate is set as 1%, then the growth factor for 20 years is 22.02. If the growth rate is 5%, then the growth factor is 33.07. For the design of the flexible pavement in Ontario, we also need to consider the average annual daily traffic, AADT. As we defined previously, AADT is an estimate about the daily traffic, and usually is measured as the total traffic that occurs in 1 year period divided by 365 days. This value includes the vehicle classes from 1 to 13 in both directions of the road. Usually we estimate AADT with the automatic traffic recorder, and the calculation about the AADT can be found by averaging the number of the vehicles measured during different time periods in each month or seasons, and weighted between the weekdays and weekends. Once you find out the ADT over multiple years, you can find out the potential traffic growth rate by comparing the historical ADT to the current ADT. Another thing we have to consider is the vehicle type distribution. Well, as we specified previously, there are 13 vehicle classes we have to consider on the road, and the vehicle class 4 to 13 will be trucks. We need to determine the percentage of the truck in the traffic stream for the base year and estimate the ESALs during the design period. In this page, we will show one example for the estimation of ESAL for the 2-lane highway in Ontario. The current daily traffic is set as 10,000, and the number of the lanes is set as 2. The design lane factor is 0.5. The total design life is 20 years, and the annual growth rate is 3%. So with 20 years and 3%, we can find out the growth factor as 26.87%. We are also provided with the percentage of the distribution for each vehicle class. Generally, we only need to consider the vehicle class 4 to 13, which will be the trucks, and 1 to 3 represent the passenger cars. For the ADT, we have 95.5% of the traffic as the passenger cars, and the rest 4.5% are the trucks. We do not have any trucks for the class 4, 7, 11, 12, and 13. Their percentage for the class 5, 6, 8, and 9 are all 1, and for the class 10 is 0.5%. With that, we can find out the current annual number of the traffic for each class. The total number of one direction is 1,825,000, which comes from the calculation of 10,000 times 365 times the design lane factor, which is 0.5. And the value in this column will be the distribution percentage times the total annual number. Also, we can find out the flexible ESAL factor, which is the truck factor for the Ontario truck number model. With that, we can find out the current annual ESAL, which would be the column 1 by column 2. And we see that this one is column 3, then the last column cumulative ESAL would be column 3 by the growth factor, that is 26.87. So we can find out the cumulative ESAL for each vehicle type, and then we summarize all the vehicle classes, and we can find out the total cumulative ESALs for this design of the pavement. In the second example, we will consider the same problem, but the percentage of the trailing hauling trucks is increased, which would be the class 7 truck. The percentage increased from 1 to 2. With that, we can apply the similar process for the estimation of the cumulative ESAL for each class, and we can find that the cumulative ESAR for the vehicle class 7 increased dramatically, and the total cumulative ESAR also increased due to the increasing of the Trident hauling trucks. With the previous information, we can then determine the thickness of the flexible pavement layers. The procedure of estimating the thickness is exactly the same to the AASHTO method as we presented in the previous lecture. While in Ontario, sometimes we have to introduce the staged construction for some roads, even though it's not quite common. The staged construction is used when the funding is not sufficient or when the traffic estimation is not accurate. Usually, the construction is divided into two stages. In the first stage, we will design the pavement structure based on the current condition, and then we'll wait for a while to detect the weak spots on the roads and fix them in the second stage. For the staged construction, the designed and allowable ESARs for stage 1 and 2 should satisfy the equation as we show in this page. This kind of design is not quite common, so we will not introduce more details in this class. Finally, we can make a comparison about the AI and the AASHTO methods. Actually, these two methods are very different due to the consideration about the reliability in the pavement design. The AASHTO method applies the reliability by using the average values of the variables, including the effective subgrade soil resilient modulus, while the AI method does not consider the reliability and uses the normal subgrade resilient modulus that is smaller than 60 to 87.5% of all the test values, and the percentile is selected based on the level of traffic. The table below shows the comparison about the thickness from the AASHTO and the AI methods. Basically, you can see that the AASHTO method will estimate the thickness with a higher value compared to the AI method. We can recall one example in the previous lecture for the estimation of the effective resilient modulus. The table here shows the resilient modulus estimated for each month over 1 year. With the AASHTO method, we find out the effective resilient modulus is 2200 psi, while for the AI method, when we consider 60% higher, the value of MR will be 4500 psi, which is much higher than the AASHTO method. So that's all about lecture today. Thank you very much for your attention. With that, we finished all the contents in the flexible pavement design. In the next lecture, we will introduce the rigid pavement design.